bold. Address 22. What line of cache is 22 going to be stored? Well, 22 written in binary looks like this. And you say, I can't do that. And I say, it's not that bad. It's 16 plus what? 22. 6. 16 plus 6, 22. So here's 16 and 6. Why am I going to look at this last 3 bits? Because it's given that this cache has 8 lines. What line of cache will this data be stored? You got it. So we said this thing was empty. Okay. Is it a hit or a miss? Well, that's what we also actually call a compulsory miss. There's different types of misses. If it's the first, ever reference and the data is empty in cache, it has to be a miss. It's compulsory. So this is a miss. Okay. And what we're going to do here is on this is also called memory reference address trace. We're going to trace memory references and look at what happens. We start out with cache empty. We're going to write in here what data is stored. Okay, so mem of 22 is the jacket that has the 22 tag attached to it. Is that making sense? 22 is the address, that's the tag. Mem of 22 is the data at memory address 22. So after we do that reference, right, mem of 22 is sitting in cache line number 6. 6 numbered 0 through 7. Then what? You reference 26. It's going to be compulsory miss again, right? But what cache line is this stored in? Well, what's 26 in binary?
116, 180.
You got it. So there it is. Line 2. Okay. Question is, what did we store here? I kind of glossed over in the previous, but what did we store here? Where does this come from?
The specific number.
It's the remainder of the address bits. So question, how many bits of tag do we need? Well, if we have 8 lines of cache, you're going to need 3 bits of address to tell me which cache line. If you start with 5, you have 2 left over for the tag. If that's confusing to you, just go back to this example and code check-in, right? If there's 4 decimal digits and the last one's used for the bin, what is he attaching to your jacket? We may attach the whole thing, but the only thing that really matters is the first 3 decimal digits. It's the bits that are left over, the digits that are left over. What digits do we have left over? Well, we need 3 for the line of cache. We have 2 left over. So where are we going to store those 2? We're going to attach the tag here. Why would you want to do that? We're going to keep going on this calculation, but before we do that, why is it important to store these upper bits? Yeah, go ahead.
So we could retrieve it from memory.
So when we retrieve it from memory, we check it's the data that we think it is, right? Because there's multiple things that map to that line. Just because, like I said, somebody checked their fur coat, leather. Okay, that's not my style. So leather jacket. Okay, so somebody I check my leather jacket, but somebody just checked a cheap thing. So I want my leather jacket back, not the cheap thing. How does he know if it's my jacket or not? He's got to look at the tag. In other words, a lot of addresses are going to map to this same line. Later, you have to look back and say, which data is that? Which address? We need to look at the tag. Remember, the idea is we're going to store data here, and hopefully we use it in the future. That's going to be a hit, so let's try. So I'm just putting 2 in one slide to save time, or to save photons, I guess. So address 22 is referenced in 26. So 22, hit or miss. So we got to look in which line of cache. Line 6. Line 6, we see there's some data there, but is it the data we look for? What we're going to do then is compare the tags. You're looking for 1, 0 in the tag, you found 1, 0. It's a hit. You're good to go. Okay, what about 26? 26, we just had 26, right? So guess what? We're going to go to what line? Okay, and then what, we're going to compare tags? You're good to go. Hit, hit. Then what? 16, 3, 16. So 16 is which line of cache? 0. And there's the tag. It's got to be a miss. Okay. And then 3 is going to 3. and then tag of 0, okay, it's also a miss. And then 16 is referenced again. Okay, this is from left to right, just like we read letters on the page. And this address 16 is referenced again. We're going to do what? We're going to look in line 0 and then match the tag. Tag matches, it's a hit. Okay. Last reference, all right, yeah, 18. Last reference, 2. Oh, there's data in 2. Is it a hit? No. And you're right, and what? Tag doesn't match. Okay. If you look there, this is looking for 1, 0, right? 18, but this is at the final state, right? The previous state was 1, 1. So that was a miss. Okay. Miss. Then after this is showing the final state after it's updated, which is always a confusion. Just know that this is what we're just depicting here is the final state after this transaction occurs. Yes,
so
sir.
In data there, is that like actual data that they brought in, or is that like a pointer to like a memory address?
Can you?
In your data line here.
That's the actual data. So this is.
Okay, so that's actual data pulled from memory.
So we're just to make it traceable in this example, we're calling that data, we're referring to it as a name mem of that. But that is, the jacket that has tag number 2105. That's like saying jacket with the tag 2105. It is data. It is data. So that what we're seeing here is inside the cache, we have data, which is the actual data values, and we have tags, bits. We have data bits in cache. We have tag bits in cache. Data bits are values. Tag bits are address bits. Are they the full address? No, only a few. Why? Because some of the bits of the address are a mod function to tell us where to store it. We don't need to store it. You can store them, but it's redundant. So we don't waste the bits. Want to try another example or ask questions? Or yeah.
What's really like the significance of the hit ratio if it's just saying like that's how many times?
Yeah. Okay. So this is good because so in other words, how many references occurred in this example? 8. And how many times do we find data in the cache? 3. So that's 3/8 is the hit ratio. So there's hit ratio, and hit rate. Hit ratio is a little letter H. Goes between 0.0 and 1.0, less than or equal. Okay. We call it the hit ratio. And then ration. If you multiply times 100%, you end up with what we call the hit rate. They're actually kind of the same, right? But sometimes people use the word hit rate, the kind of default to that, but not 100% used. It means this would come to 37.5%. Is a hit rate. But what's the significance of that? Well, okay, so this cache design has a hit rate of 37.5, and another cache design has a hit rate of 90%. Okay, go back to your store. If you went to Publix, you only found a cache lien on 37% of the time, and you go to Walmart and you find it there 90% of the time. If the prices are equal and everything else is equal, where do you go to shop? Walmart. So what we want to do is we want a highest hit rate as possible because the hit rate is telling us the efficiency of this cache, the effectiveness. Does it make a difference? It makes a big difference and it's nonlinear because why? Because, sorry for so many clicks. What's that?
Is it the 90-10 rule?
90-10 rule is getting us there how to organize this, but why is it important to have a high hit rate, or why does it make a difference? Because
Less time.
Way less time, because it's 10 times faster at each level. So, if you find the data, if the hit rate's 90% versus even 70%, it's not just 20% faster. It means that 90% of the time you only took 5 nanoseconds, and 10% of the time you took 50, but in the other case, only 70% of the time you took 5, and then 30% you took 50. So what's the weighted average of that? That's going to be a lot slower just for a hit rate of 20% less. Every 1% of the hit rate, right, is multiplied by a factor of 10 here. Hit rate's very key. It's a really good metric for us to get, like, get one number, right? One number. How effective is the cache? Hit rate. Yeah, hit rate is going to give us a good. Since we're at the end, we won't do new things, but we'll show you where we're headed, what's coming down. So we're going to give you some equations to use powers of 2 and logs to calculate the size of the cache. What's that? How many bits are total in this component? Basically, we calculate each one and add them up. Okay, that's this slide. And I killed my battery because too many clicks. And then what do we do from that? Then we're going to show you some, this is getting cool, right? We're going to show you some hardware designs. So we can see actual address bits. This is the address bus. Then we're going to start to see the fields. Take the fields, and some of them tell us which line of the cache, and then we have the data coming through, and how do we make a choice? We use a MUX to select which one of these we want to access from. We're going to design that for you next time. And then we're going to look at using spatial locality and start using more than one word per block, because we only used one word per block here. We'll do some more examples of these. If you want to look ahead of time, you can see some of these and be ready for class. Okay, there's one more question. We have time for one more question.
When you go back to that example,
which one? Yeah.
How
Good.
many tags can you fit
Okay.
in each address? Would it be 3 tags?
Oh, that's a great question. Only one. Only one. So in this, so the key thing here is that we only have, see that we were replacing these. So in other words, where do we overwrite? 16 overwrote something, right?
Oh, okay.
That's the point, is that
Replacing it.
because this is the capacity here is smaller than the main memory, so when they map to the same one, you overwrite it.
You overwrite it, and the one you overwrite stays in the cache,
In main memory it stays, but it gets overwritten in the cache.
into the cache.
Yeah, you only have space for one because main memory is small. There's the same thing back to your closet, right? So the final thing to leave you with, a little analogy, which is exactly what he's talking about, is if you're in a hurry, or I don't know, maybe you're a bachelor or bachelorette, I don't know, but like I don't even put, maybe this is too much information, but like when I do my wash, I just put things on top of the dryer, right? Gym clothes, no, I don't put it in a closet and take it out and put it back. I just leave it as temporal locality. I know, like the next day, I'm gonna, right? We all do people do this, right? I think, right? It's like so much better, right? Once you're like, you know what? Especially socks or just little things, right? It's too much. That's temporal locality because you don't have space, right? But what do you put on the cache on top of your dryer is just the stuff you're going to use a lot. It's temporal locality, but if you put one thing there, maybe it kicks something else off. Right? Okay, guys, we see you next. So now let's look at using more than one. This is going to start right. More than one word per line. In this example here, we had the word size was just 1 byte. Okay, so we actually didn't need any word bits. And then also we had that the block size, right, was 1. Which meant 0 bits for the block, the word within the block. The block size is 0 bits. What does that mean? That means that we don't capture any spatial locality. So actually, in this example, this would be going back and forth between Publix and Lakeland with just a palette of 1 item. You can do that. You can make the block size to be just 1 word, but in practice, we make it more than 1 word to do what? To capture spatial locality. We're going to come back to these calculations. Let's just do an example, then it'll make it easier. So in this example, we're going to use a block size bigger than 1. We're going to actually have 2 words per block. I need 1 bit to tell me the block number. I'm going to show you how to calculate these soon, but just take them for given right now. So assume that main memory has a total of 16 words in it. It's not a very huge memory, but something can fit on one slide. And assume cache has a total of 4 words. So you have 4 words organized such that you have 2 words per line. How many lines do you have? 2. All right. You have 4 words in total, and you're organized as 2 2 words per line, which was given, right? Which is the words, 2 words per line. So we end up with 2 lines. Let's call it line 0 and line 1. If I look inside memory, I have to address 0 through 15. It has to be mapped to only 4 words of cache. How are they stored? Well, if it's address 0 or 1, this is line 0, and then here's 4 and 5. So 0 and 1 come in on one pallet. So in other words, if the processor references address 1, I'm going to bring in a pallet of 0 and 1 and place that in order right here. If I reference address 8, 8 and 9 come in as a pallet. That's going to go into the 0th line of cache. Suppose the processor references address 11. Turns out 11 is in line 1. This is going to come in as a pallet stored here. No matter if I reference 10 or 11. But what was the advantage of moving a pallet at a time? If I reference address 11 at time t plus 1, there's a higher chance I'm going to reference nearby in the neighborhood. Right? We use Mr. Rogers in the neighborhood. So, well, if I reference 11, I might jump up and go back in the loop and go to 10. Good thing, because I already brought 10 along, right? You see, the longer or wider I make my line, the more spatial locality I can capture. But what's the trade-off?
Spacing.
You know, why not make it a billion, right? Just why not, right? Because if the pallet's too big, then you may not use the stuff that you spent the time to move over and the energy to move over, right? So there's some trade-off, there's some balance, you know, it's a Goldilocks, right? Yeah. Not too big, not too, I don't know the story, right? But you want just right, you want just right. How do you get just right? Well, that's the next class, you guys will actually do some cache studies and you can trade off these and see, does it increase the hit, what's our metric? Hit rate, right? If you see the hit rate go up, for your application, it's going to be application dependent. For your application, you run some different cases. You say if this cache size is this big, we're doing it by hand here, but there's tools that you use for the real program. You let the program run and you figure out if the cache line was only 2 words, what's the hit rate? It's going to be probably pretty low, but then you can make it a little bit bigger and watch it go up. If you make it too big, the cache hit rate's still high, but what happened? The transfer time is getting too long because the block, your packet size, right? The packet, you can think of it like a packet in a network, is transmitting too much data that you never referenced. So before we start to crunch the numbers to try this one on the next slide, does anybody have a question what this is representing? Is this outside the processor chip, or is this inside the processor chip or outside? It is inside. And you're right, and how did you know that right away?
Cache.
It is cache. Cache is always inside the chip. So imagine that we're transferring data from main memory into cache, so that something's out here in Lakeland. This is your Publix. Here's the pallets coming in. You want to try? So here's a reference string. 0, 1, up to 3, 4, so on. What's sought is to find the hit rate. So we have to look at this trace and figure out if it's a hit or not. So initially cache is empty. These are the tag bits. The tag covers the entire line. How big is the line? 2 words? Okay. So the first reference is address 0. Is a miss. It's a compulsory miss because it was empty. Cache was empty. You can't find in cache. Yeah, good.
So in these, a block would be 4 words.
Block is 2 words in this one. Block size and line size are always the same. So we said here 2 words. So block and line is the same. How do you know that? They use 2 different words for the same thing. But line means that the pallet is already in cache. Block means it's out in Lakeland. But the pallet's the same, right? Unless something fell off the truck. You know, whatever you start with is what. So block and line, I say it here, right? Block and line is like I know people is always. I bounced it, I think, even, right? Because I know it's like a important thing. Is always equal, block and line. So 2 in this case. Pallet size is 2 words. So you're getting the hint there. This is a little complicated. It's not hard, but there's a lot of words, there's a lot of terms. So what do you have to do? You got to practice the problems, and the night before might not be the most Yeah, I know. Right? I tried it. It didn't work that good for me. So first reference has to be a miss because cache is empty, but then we're going to put something into cache. The question is, what? We have a battery issue because I've probably drained it flashing back and forth there. So we're going to bring in a palette. Even though I referenced address 0, I'm going to bring in 0 and 1. Why? Because I actually use the word buddies. It is capturing spatial locality. And we're going to see that happen here because I'm going to reference address number 1. It's going to be there. Hit or miss? Hit. Why? This is the first time I saw 1. So this is where the people didn't come to class. I see it every time. They look at this. Oh, I didn't see. They just think like it's like a, I don't know, contact list in your phone or something. Oh, I never called him. He's not in the recents. I don't see 1, so it's got to be a miss. Well, no, we're transferring a block, 0 or 1. Due to spatial locality, you were awake and you got it, right? It's got a 1 is already there because you brought it, because you missed on 0, you brought 1 with it. So now you reference 1, you got a hit. This is showing how spatial locality can increase the hit rate. The higher the hit rate is, the faster we're going to execute because we're not waiting for slow memory. What about the next reference of 2? It's got to be miss. We haven't earned it because it's not part of the block. Then what? This is showing the initial condition. Why is it a miss? So this is what we're going to end up seeing here. This is the address written in binary. Okay. So byte address 2, this is binary 2, is contained in which of these blocks? Now what's interesting about this is you can look at these bit fields. This 0 or 1 is bouncing back to do what? That's left or right. So this least significant bit is telling me left or right. If the bit is a 0, it's in the left word of this line. The left word of this line. If the bit is a 1, least significant, is a 1, it's the right word of this line. Which line? The next, how many bits? Interesting. I have 2 lines. How many bits do I need to tell me the line number? Just 1. So this is going to be line number 0. Is based on this bit. So if I see a 0 here and I see a 0 here, it's going to be line 0. I get to here, this reference is going to be line number 1. What are these bits? They're the tag. See these upper 2? Tags what's left over. So the least significant bit in this your question you're asking is our conclusion from doing this exercise. We'll just give you the answer, then we'll look at it. So here we have 4 bits of address. This tells us the word within the line. And this is telling us the line in the cache. Right? This bit is either a 0 or 1. This bit is either a 0 or 1. What about these 2 bits? They're either 0 or 1. That's the tag. This tag of 2 bits. We can see the tag written here as the upper 2 bits of this reference. You reference 001. So the tag gets written here. This next bit 0 is telling you the line in the cache. This is either what? Either above, top or bottom. Okay. And what is this? Left or right? You're going to say why. It's actually how they hooked up the circuit, but we'll take a look. So let's try the next one. So this is what we start with in cache, but then we're going to load into cache the line that we missed. We missed on memory address 2, but 2 is paired with 2 and 3. How do I know that? Because it's got to be the leftmost cell of the bottom line is memory address 2. What about 3? 3 is going to be a hit. Where do I find 3? Well, I'm going to see if the tag matches. See, 00 happens to match the 00 tag that's stored where? In the lower, which is 1, bottom, line of this cache, I said check the tag, but where I get the data is going to be on the right side. So the address tells us exactly where to find the data. You're going to say, like, that's like so confusing. But if I gave it to you in decimal, you would know exactly what to do. You go to the code check, you know, it's your first, I said, you know, it's your first day on the job. How would you design that system? Well, you know, by the first week, you just put them in a pile, right? And then if you don't improve the second week, they find somebody else, right? But what do you do? Well, you know what? Five over here, right? Because these guys come quick, right? Nanosecond memory access, right? They all want their service quick. You want to get a tip, so you come up with direct map in your head. I think we all do it, right? Okay, 5, that goes there. 3, you just look at the last digit, right? This is looking at the last bits. We're going to look at only one bit at a time. Let's give it 2 choices. It's the simplest case. This lower bit is telling us left or right within the palette. This is the location within the palette. 0 is they just make this mapping over here on the left. And if it's a 1, it's in the right of the top, which is the next bit, 0. If that goes to a 1, you're going to be in the bottom, which we saw here. 2 goes in the bottom. Does that answer the question how they get it? Okay. So now let's try the next one. We have a battery issue. So now this is the initial condition. I just copied this, right? From here to here. Hit or miss? It is a hit due to spatial locality. And then 5, hit or miss? Miss. So how did I know it's a miss? So a human being can look and see that there's no mem5. How did the hardware do it? Well,
Line 0 tag didn't match.
You got it. Line 0's tag. Okay, so exactly. So 1 is telling me it's going to be the right. This is going to be line 0. I compare this 0, 0 to the upper 2 bits here, 0, 1. No match, no deal. It's different data. Somebody else's jacket. You're going to say, whose jacket was this? Well, this was actually the 0, 1 palette, not the 5 and 6 palette. We can go through and keep doing this. This is a good example to do. Well, here we had to replace, right? So actually, since we had this is the point of direct map. There's only one place to put it. We don't have infinite bin size. So the difference between, this is where we diverge a little bit from our analogy. Once the bin is full, I got to throw out somebody's jacket to store the next one. So I only have storage for one set of bits at a time here. So memory is going to overwrite it with a new value. So I overwrite the contents of mem0 with the contents of mem4. That's data, right? And then I update the tag. The point is, if I went through this process, we saw some examples, right? This is an example of spatial locality. We have a hit, even though we haven't seen it already in the reference string, thanks to spatial locality. We'll get happy. This, we can calculate hit rate, I think, at the end. So hit rate, we had 8 requests, 4 misses, so hit rate is 50%. Suppose you did not have 2 words per block. Suppose you had just 1 word per block. You did not try to capture spatial locality. What would the hit rate be? Well, we're going to miss here. We're going to miss here. We're going to miss here. Then you're back to your recents on your iPhone. Right? Yeah, only 1. Does the spatial locality work? In a lot of cases, right? You can always come up with a counter example, right? If you guys like puzzles, there's something called Bilaty's anomaly. Did anybody know that one? The operating systems, sometimes they cover it, but we see it in cache too. Sometimes when you make it's a very rare reference string, you have to almost manufacture it, but there are cases, if you make the cache larger, the hit rate actually goes down. It's very strange, but it happens in very strange cases where if you make it, it's kind of like back to this harmonic. Remember we said a beat frequency? So what happens is, because of the size of it's a mod and it mods around, whatever you got rid of is exactly what you want. If it was a little bit smaller, that badness wouldn't happen. So generally, when we make the cache larger, the hit rate goes up. Generally, when we make the block size larger, the hit rate goes up. But the transfer time may go up too if we make the block too large. Any other discussions on this? We can try some more examples. Yeah. Oh yeah, this is it's a
It's the number of lines or it's the size of the line?
number of lines. It's so counter. Matter of fact, I remember the first time I saw it this is when you start to get interested in your field, and it's like you say, you know what, this is like, I want to go to graduate school and like do these cool things. Is Blady's anomaly. I remember I kept coming back to it. It's like, really? And then you can see it's true. Let's see. We'll Google it here. We'll try to give you the right name. I think it's B.E. It's some guy's name, actually. He wrote the paper. Blady's anomaly. There we go. Oh, there's even a wiki on it. Sometimes wikis, just to get the first level, is good. So here's an example of Blady's anomaly using 3-page frames. And we have 9 page faults. So page fault is a miss. A page is the same as a line, but it's in the operating system instead of cache. And then if you went to 4, so you actually made the cache bigger, you increased it from 3 to 4 lines, you actually have 10 page faults. And the point is that whatever you requested, it just happens to get replaced right before it.